Okay, so far in vectors, we've mainly been looking at defining them and talking about the various properties. So things like how do you add vectors together, how do you multiply a vector by a scalar, what are position vectors, what are unit vectors, what is the magnitude and direction of a vector, what are all these various properties and how do they relate to each other. But we haven't really been using them to actually solve questions or to solve problems. So that's what we're going to start looking at a little bit now. Specifically, as the title says, solving geometric problems, which is one particular type of problem that vectors can be used for. So we're basically going to start using them as they were intended to be used, at least on some initial problems. Now, in order to do this, there's one particular technique, let's put it that way, that we can use a lot when we're working with vectors, which is shown here in this example question that I've got here on this first slide. It's this idea of having a point that's part way along a line that's created by two other points, and how to express that mathematically. So the idea here is that you've got, say, a point A, and you've got a point B, or in this case I've said C, haven't I? And the point B, it could be here, it could be here, it could be over here. It can't be here, right? It's not allowed to be there. It's somewhere on that invisible line connecting A and C, right? It's somewhere on that line, but we don't know where. So we're given some information, but not complete information. We don't know exactly where B is, but we do know it can't be just anywhere in the 2D plane. It's somewhere between A and C on that line. How do you write that mathematically? There could be multiple ways, but we want to write it now using vectors and lambda notation. So have a think about it. Don't just skip to the answer. See if you can figure it out yourself first. How do I express this mathematically? That B is somewhere on that line. Have a think. You can pause now. Okay, so assuming you paused, the key here is to think about the following two vectors, AB and AC. Okay. This technique might work with another pair, but let's pick these two. Look at the vector AB, and then let's look at the vector AC, which is there. And what property do they share, or what property or relationship do they have? They're parallel. And if B was not on that line, let's say B was over here, then they wouldn't be parallel anymore, right? The lighter green would be going over there, and the darker green would stay where it is. They wouldn't be parallel. So saying that those two vectors are parallel is equivalent to saying that the point B is directly between A and C on the line connecting them. So we've converted the English sentence into this statement: AB and AC are parallel, which is still partly an English statement, right? So these two are parallel. And now let's go even further. I don't want those words "are parallel" there. So going back to what you've learned about parallel vectors, how do we describe this mathematically then? Here's the final answer. AB is equal to lambda AC, where lambda is some number. I don't know what it is. The lambda value is going to change depending on where exactly B is on that line, right? If it's in the middle, then it'll be a half. If it's a quarter of the way along, it'll be a quarter, and so on. But the fact that there is such a number tells you that those two vectors are parallel. If you can't quite remember why this statement is the same thing as saying that the two are parallel, then you're going to have to go back to the previous video on that, where I talked about parallel vectors. Okay, because that is effectively a fundamental definition. Two vectors are parallel if one is the scalar multiple of the other. Okay, so that's it. And this is you're gonna need to use this. So make sure it makes sense to you before you proceed. The point B being between the points A and C is the same as that statement there in purple, right? And that we've used there about 6 characters rather than the 100 or so that we've used in that 2 sentences. So it's quite efficient. Right, so let's look at some examples already. Actually, I want to start with an example because hopefully it starts to clarify how we make use of what we've just talked about on the first slide. So you've got a diagram, you've got the points A and B, and they have position vectors little a and little b respectively. So they've just given us for free some extra names in there. Okay, so remember, capital A is a point, little a is the vector, which is OA, and little b is the vector OB, capital O, capital B. Referring to the origin O, they don't have to say that. It's standard that O is the origin. The point P, this one, divides AB, that line, into the ratio 1, 2. Find the position vector of P. Okay, so this is all about, and here's the key, this is all about convert the information you've got into a mathematical statements, convert what you've been asked to find into a mathematical statement, and then just work with the mathematics and forget about all the English and whatever language your mathematical problem's in. You want to be working just with mathematics. So let's do that initial conversion step. The point P divides AB in the ratio 1, 2. That's a bit of information. Let's convert it into mathematics. So first of all, P is on the line between A and B. So from what we just talked about, I can say the following. AP is equal to lambda AB. Okay, hopefully we're in agreement there. So this statement tells me that P is somewhere on that line. However, we can go one step further, because we've not only been told that it's on the line, we've been told that AP and PB split the AB line into this ratio 1, 2. So in other words, we've got the following ratio. Let's do this. Let's make sure I do this the right way around. 2 times AP is equal to PB, right? Or 1 times PB, right? That's the 2-1 ratio. Okay. So just to make this clear, to put this in English terms, this first line is saying P is on the line AB, as opposed to not being on the line at all. And the second statement is, I won't put it in quotes. Let's put it in quotes. Where P is on the line. Okay. So first statement tells me it's on the line. Second statement tells me where it is on the line. And then notice. Oh no, that's fine. Yeah. So then that's our first 2 bits of information. Okay. And now let's look at this thing. Find the position vector of P. In other words, do the following. Position vector of P is this. What is it? Okay. So we've got this nice little box now of mathematical statements. Okay. The third of which is just, here's what you need to find. What is OP? Okay. Now we could potentially look at the diagram at this point, and let's think. Okay, OP, what is that? Let's pick a different path, right? Because I don't know what OP is. Is there another path? Oh well, I could go from O to A and then A to P. Okay, so let's do that. O to A from A to P. So I can then write this. Okay, those are the same. So OP, I've now changed the problem slightly. Now notice this one, OA, that is little a, right? That's this thing here. So let's write that in. So it's A plus AP. Okay, so we're halfway there because that OA we've converted into this little a, which we can't simplify any further. Our final answer is going to be in terms of little a and little b, right? But this AP, we now need to do something with this. Okay, so let's have a think. There's something we've kind of missed, which is it's obvious, but we didn't write it down in our list of mathematical statements, and it's the following: AB, right, which is this thing, is the same as AP plus PB. Let's write that down. AB equals AP plus PB. Okay, now at the moment it just looks like a mess of letters, and it's like which ones are relevant and which ones aren't. So let's see if we can kind of work backwards from what we have to what we want. So we have AP, but that isn't defined in any way. It's not defined in terms of little a or little b. However, OA is, OB is, and also AB is, because AB is the following. It's AB is the same as going from A to O and then O to B, or in other words, minus A minus little a plus little b. Okay, so it's this. Okay, pause and double check that makes sense to you. AB is little b minus little a. So if we could somehow rewrite AP in terms of AB, then we could substitute that in and we'd be done. So can we do that? Well, we've got AP here, and it's got an AB here, but then we've got this PB. So then we'll have to figure out what that is. But then that PB is here, which is written in terms of AP, which is what we have. So we're going to basically combine these two bits of information somehow. Okay, we're going to make use of those. So let's go over here, and we're going to say right, AB, and I'm working with this bit here and then going along, is equal to AP plus PB, and PB is the same as 2AP. So it's AP plus 2AP. So in other words, AB is equal to 3AP. We're almost there. So then AP is equal to a third of AB. Now I'm just going to pause for a moment, because perhaps if you had done this yourself, or you got a bit ahead of me, you might have already come up with this statement yourself without doing what you might think is quite a complicated bit of arithmetic and manipulation. All that is saying is that AP is a third of the length of that AB, which makes sense. If it's a 2:1 ratio, then the AP is going to be a third of the AB. The only thing is, although it's good to be able to write that immediately, and that is fine if you can, just because we're new to this potentially, I think it's good to remember why it is the case that we can get this result. And ultimately it's from this, from considering that the total is the sum of two parts and that we have this ratio. Okay, but we've got that, and now we can substitute that AP, which is this, into here, and we'll basically be done. Just before we substitute, let's change that AB into what we know it is, right? AB is B minus A here. There we go, B minus A. So then let's go back down here, bottom, we've got A plus AP, which is a third of B minus A, quite a few brackets there. If you multiply that out, you'll get a third B minus a third A, which should, let me double check, indeed simplify to 2/3 A plus a third B. And we got there. There's the answer. Okay. So if that confused you, if you found any of that a bit difficult, you weren't quite sure where certain numbers came from or why we did things a certain way, feel free to ask, or just rewind a bit and see if you can follow along. Okay, but hopefully that made sense. So we've answered the question, find the position vector of P, which was OP, and in this case we had no numbers, so to answer that we just wrote it in terms of what we were given, which is the little a and the little b. When you're ready, let's go look at another example. Actually, just before the example, one quick thing which you're going to be making use of is this idea of comparing non-parallel vectors. It's not as complicated as it seems. Let me throw out an example for you. If I said to you, I've got one vector 5i plus 3j, and it's equal to ai plus bj. What is a equal to, and what is b equal to? It might seem extremely obvious. A is 5, b is 3. And in fact, that is the answer. But there's a small technicality that you need to be aware of that allows you to make that assumption. This only works because I and j are not parallel. They're not parallel, so then you can do this. If they were parallel, then the a and the b could be many different pairs of values. You'd actually have infinite possible solutions, right? Because effectively you'd have on the left hand side 8 of something, because they're parallel, you can add them up. And then on the right hand side, as long as you pick any a and b that adds up to 8, you'll have a possible answer. So this only works for non-parallel vectors. And this is also the case then, even if it's not I and j, if it's any vectors. Okay, so let's say now I've got two vectors a and b, and now don't get confused, the previous a and b were numbers, now I'm talking about vectors a and b. Let's say a and b are vectors and they're non-parallel. Okay, so if you pick any two vectors at random, they're probably not going to be parallel. So this is going to work almost all the time, as long as these two aren't parallel. Then we can make the following statement. If I have a multiplied by some number, let's say p, and I add to that b multiplied by some number, let's say q, and I then say r multiplied by a plus s times b, you might be wondering where I'm going with this, but let's say we do this and we create two new vectors by combining a and b in two different ways. That's why I need so many letters, p, q, r, and s. If those two happen to be equal, the whole thing, then that implies that p equals q and r equals s. Again, it might seem super obvious, but this only works if A and B are non-parallel. Okay, so an example question could be 5 times A plus 3 times B equals RA plus SB. What are R and S? They're 5 and 3. Okay. In the majority of cases, this is almost going to be something you were doing anyway, or if you didn't know this rule, you probably were using it. But it's just important that you remember, because it might catch you out one day. You can't do this if A and B are parallel. So that's all I really want you to take away from this. Okay. You can equate the coefficients of these combinations of vectors as long as they are not parallel. Cool. All right, let's look at an example now. Let's actually look at an example. Okay, so this example, this is a proof question. I know students don't always like proof stuff, but that might just be because you're not quite familiar with just how great it can be. But in this case, we're proving something which might seem obvious, but technically, if you haven't proven it, you haven't really shown that it's necessarily the case. And that is the following. We're going to prove that if you take any parallelogram, doesn't matter what kind of parallelogram it is, and then draw a diagonal between two opposing sides and a diagonal between the other two opposing sides, that the lines will bisect each other. Now, an important point here is that we just want to distinguish the words bisect and intersect. Okay. Intersect is almost too obvious to even bother proving. I suppose you could, but clearly the two lines are intersecting. However, when we say bisect, what we're specifically saying that is that that intersection point is halfway along the line OB and halfway along the line AC. And then that's the key thing that we want to show. That's what we want to prove. Why is it a half? It could have been a third. It could have been, 3/5. It could have been, so anything. But it just so happens for any parallelogram, it intersects halfway along the line. Halfway along both lines, in fact, AC and OB. So that's what we're going to prove. I'm just going to look at the wording of the question to just double check we've understood this correctly. So OABC is a parallelogram. So in this case, O is our reference point. It's an origin in some sense, but really it doesn't matter in this context whether they're position vectors or regular vectors, as long as we've got all the points named. So that's our parallelogram named. P is named, which is the intersection point. Then we are told the following: the vectors little a and little c are equal to OA and OC respectively, which is standard convention. Let's just write that on then. So that's little a going that way, and this one's little c here. Prove that the diagonals bisect each other. Right, so indeed we're going to prove what we thought we were going to prove. Now the thing is, the fact that we call this little a and little c, that doesn't actually matter if we did that necessarily or not. The reason the question has told us that is presumably to give us a little bit of initial help, like a kind of clue as to what we're going to do. So first of all, let's define, or let's think about what is it exactly we want to show mathematically. Remember, we want to put everything in terms of mathematics. In some sense, there's multiple ways we could define it, but in some sense we want to show the following. We want to show that AP is half of AC, which means it's intersecting halfway along that line, and we also want to show that OP is also half of OB. So it's halfway along that line. Okay, we'll see what happens. We might end up getting this set of statements, or maybe we'll get something that's equivalent. But this is the kind of thing we want to be showing. Okay, so prove it. The way we're going to proceed is about thinking about multiple paths. So, for instance, we've got AP equals half AC. That's what we're aiming for. Now, P is definitely on the line AC. So we actually know for a fact. So now I'm going over to the left, and now I'm just going to start with what we actually know for sure. Right? This is our target. Right? This is what we want to prove. We know for a fact AP is equal to lambda AC. Right? Or let's say lambda 1. Right? And we know for a fact that OP is equal to lambda 2 OB. Right? I've called them lambda 1 and lambda 2 because I don't know if they're equal. I know by the end of it they will be. I know they're going to end up being half-half because I happen to know the answer in advance, right? That's what we're trying to prove. But at this stage we're proving something we can't assume. So these statements are just saying P is on the line. Right? P is on that line AC, P is on that line OB. That's what that statement's saying. So I don't need to prove that. That is by definition of intersection. P is on both those lines. So now with that, we're going to see if we can figure out what is lambda 1, what is lambda 2. And the way we're going to do that is by coming up with multiple ways of expressing this path, a path to P. Okay. So let's try it. And these are the paths I'm going to pick. I'm going to pick one path, let's call it the blue path, which goes along one of the diagonals. And then I'm going to pick a different path, let's call it the green path, oops, which goes along one of the other diagonals. Okay. And both of those are representative of OP. Right? They're exactly the same start and end point. Let's work out what they are. In the blue case, it's little a plus AP. In the green case, it's just OP. Okay, where are we going with this? So let's now use what we defined up above with the lambdas. So in the blue, we've got A plus, well, AP is lambda 1 AC, and for the green, we've got OP is equal to, well, can we simplify it any further? Oh yes, we can. Immediately we just plug in the lambda 2 version, lambda 2 OB. Okay. And now notice this. Okay, a lot of techniques we're getting here. The reason why that's useful is because we can express both AC and OB in terms of our little a and little c. Can we see that? So let's look at this one first. Big A to big C. That's this pathway there. I'm marking out. If I start at A and I go minus little a plus little c, I end up at big C. So that's a pathway, right? Let's make a note of that pathway. Let's make a note here. AC is the same thing as minus little a plus little c, which is the same thing as little c minus little a. And therefore, we can rewrite this one as a plus lambda 1 times c minus a. So now we've defined the blue path entirely in terms of little c's and little a's. Right, now let's try the green path. See where we get with that. The green path is lambda 2 OB. What is OB? Well, notice this. Because this is a parallelogram, and now we're going to use the fact that it's a parallelogram, OA is exactly the same as CB, right? Same direction, because it's a parallelogram, they're parallel, and same length, because by definition, within a parallelogram, opposite sides are the same length. So therefore, this is also little a. And by similar logic, this up here is also little c, right? Going in the same direction. Let's make the directions the same. Let's match them up. The opposite sides have the same direction. So therefore, OB, this path from O to B, is the same thing as C plus A, or equivalently A plus C. Same thing. So let's go with A plus C because it's alphabetical order, and then let's replace it here. Lambda 2 A plus C. Okay, we're almost there. So these are our two key statements. OP is equal to that I've underlined, and it's also equal to this. So if I've got two expressions for the same thing, I can equate them. So let's do that now. I'm just going to clear up some space first. Let me just fast forward in time. So I've just kept there the two things I want to equate, and I'm going to write it up here at the top. Lambda 1 times C minus A is apparently equal to lambda 2 A plus C. And oops, I just missed off an A plus here. There we go. Okay, now think back to what I was saying about the non-parallel vectors. If I have two vectors and I multiply them, add them together, and I do that in two different ways, if those two different ways are equal, then the coefficients, what I multiplied by, are the same. So that is me just reiterating what we looked at before on a previous slide, the non-parallel vectors. Okay, so you can go back and look at that if you're not quite sure what I'm talking about. Why that's relevant now is we're going to multiply out both sides of this red equation to get everything as a multiple of A plus a multiple of C. So on the left hand side, I've got 1 plus lambda 1. Is it plus? No, it's minus actually. 1 minus lambda 1 times little a plus lambda 1 c. On the right hand side, I've got lambda 2 a plus lambda 2 c. And now we can equate coefficients. Because a and c are parallel, are not parallel, because they're not parallel, we can equate these coefficients. In other words, we now know for a fact 1 minus lambda 1 is the same thing as lambda 2. These are equal. And we also know that lambda 1 and lambda 2 are also equal. So let's write that down. One minus lambda 1 equals lambda 2, and also lambda 1 equals lambda 2, right? Simultaneous equations, if you solve that, you'll end up with the following. Lambda 1 is the same as lambda 2, that we know, and then both must be a half. Okay, that's the only conclusion you can make from those two equations there, that they're both equal to a half. And there we've got our key number, 1/2. So I've rubbed it out, but if you go back and you can see how are these lambda 1 and lambda 2s being used, we were saying that OP must be lambda 1 or lambda 2 of OB, and AP was a lambda times AC. In both cases, those lambda were a half, so we've shown that P is halfway along one diagonal and halfway along the other diagonal. Therefore, the diagonals bisect. Okay, if that seemed like it was needlessly complicated, it isn't. That is actually a full and rigorous proof, and you can't really get much simpler than that without coming up, I don't know, maybe you could invent your own notation, but if you want to prove the diagonals of a parallelogram intersect, this is how you're going to do it. It's a little bit tricky, I think, the first time you start seeing stuff like this. So don't fret if you find it a bit hard to follow. But if you have found it so difficult that you're lost, go back and get back to the point where you first start struggling, and then ask me, right? And I'll help you along. Okay. Every step there is some logic to it. So you do need to be able to follow it. If you have been able to follow this, then great. I think this was the hardest example out of the three I was going to do. One final example, and it's a quick one. It's not proof, but it's just using another bit of mathematics that you might have forgotten about. It should be a quick one to get through. Let's take a look. Okay, so this is our final little example. So I guess it's just a bit of a refresher or a reminder that just because you're working with vectors doesn't mean you can't use all the other mathematical tools that you've learned so far. So for instance, in this question, we're being asked to find the angle BAC. So that's this one here, isn't it? What is that angle? And you've been told AB is 3i minus 2j and AC equals I minus 5j. How are we going to find that angle? There's actually there's two different ways of doing this. I'm not going to go through both. Perhaps you can spot the other if I go through the simpler one. So what you want to think is, right, if I've got an angle in a triangle, I don't know what it is. How can I get that value? In this case, what we could actually do is find the three lengths of the triangle. How are we going to do that? Well, AB is just going to be the length of the vector AB. So that's the square root of 3 squared plus 2 squared, right? Which is root 13. AC is going to be the square root of 1 squared plus 5 squared, root 26. And then what about BC? Well, we don't have the vector BC, but we can get it, right? So if I want a vector that starts at B and ends at C, let's follow a different path that goes along lines that we know. Start at B, we go to A, and then from A, we go to C. And that's the same as BC. So it's going to be B to A to C. So BC is equal to going from B to A plus A to C. And AB is equal to minus 3, 2. Okay, notice, I mean, I'm sort of jumping in the working now because I'm hoping you can follow it. AB is 3 minus 2, so BA is just taking the negative of both of those coefficients, as we talked about before. So that's minus 3, 2, and then AC stays as it is, it's 1 minus 5. Therefore, this is equal to minus 2 minus 3. And therefore, we can find its length. Square root of 2 squared plus 3 squared equals, it's root 13 again. Okay. Okay. So from there, if you've got three sides of a triangle and you've got an angle, then there's a certain rule. Can you remember what it is? To get the angle, I'm going to use cosine rule. So a reminder, in case you forgot, the cosine rule says a squared equals b squared plus c squared minus 2bc times cos of capital A, where in this case the a and the b and the c, those are side lengths, and remember the capital A is the angle. It gets a little bit fiddly because that rule, as I've written it, is using letters which have already been used in our specific example. So try not to get yourself too confused with that. That capital A is not the same as that capital A here. Here it's a point, and it is throughout all of that working, but in that formula, the A is the angle, it's the theta, effectively, that I drew here. But that's just because this is how the rule is expressed. So you'll just want to write it in your own way, which is to remember that the big A, the little a here is the longest side, so that's root 26. So then we can finish it off. We can say root 26 all squared equals root 13 squared, and you can see this is going to come out quite nicely because the roots are now going to go away. Minus 2 times root 13 times root 13 times cos of the theta. Okay, so I won't solve it. You can work that out quite quickly, I think. You multiply the radicals, you square the square roots, rearrange, do an inverse cos, and you should end up with theta being equal to 45 degrees in this case. Or in other words, cos theta, because it's a nice number, cos theta would have been 1 over root 2. Or root 2 over 2, same thing. Okay, great. So hopefully you've, I've not lost you. Hopefully you've managed to follow those examples. Let's have a go at the questions. Okay, so there's 2 practice questions on this slide, and then 1 more on the next one. I think, for instance, 3 would be some very good practice. So if you're low on time, you can just jump straight to 3, but if not, I mean, it's always better to do as many as you can, because you're not doing yourself any favours by not attempting the work. So give it a go, see if you can do both of them. Don't forget answers. I think I reminded you in the previous video. Look them up there. Okay, so you can pause the video now. Oh, sorry, I should just say, because I think my face is covering it, over here, that corner of the triangle, it's labelled with a capital B. Okay, that's B in the corner there. Okay, now you can pause the video. Okay, and then the final slide. This is it's another bit of practice on similar to that parallelogram bisection question, except here it's not about bisection. It's about showing that it's not a 1-1 ratio; it's a 2-3 ratio. Okay, these are quite tricky questions, especially the first time you're doing them. But don't get disheartened. See if you can get as far as you can. Ask for help if you need it. Okay, you will eventually understand it if you put your mind to it, if you allow yourself to focus and you give yourself the time to work on it. Okay, good luck. Let me know if you need help. You can pause the video now.